I would like to linger a little bit more on the chain rule, in particular in using it with polar coordinates. Let me remind you, first of all, what we did last time. X equals R cos theta, Y equals R sine theta. The picture for this, a generic picture, if your point is in the first quadrant, is that this number here is X, this number here is Y. So if you've got a right triangle like this, where this distance is X and this is Y, the hypotenuse has length R, and the angle theta is the angle with the positive x-axis. And you can derive these two formulas using SOHCAHTOA. Sine of theta is Y over R, because that's opposite over hypotenuse. And cosine of theta, adjacent over hypotenuse, is X over R. And that helps you come up with these. But also from the Pythagorean theorem, R is the square root of X squared plus Y squared. And theta, well, this is a little funny. It's, if you want to be extra precise about it, it's arctangent or inverse tangent of Y over X if X is positive, so that you're in the first or fourth quadrant, because arctangent always gives you an answer back between negative pi over 2 and positive pi over 2 radians. It's actually arctangent of Y over X plus pi if X is negative. And if X is 0, it's either pi over 2 or negative pi over 2. If X is 0, it depends on whether Y is positive. This is if Y is positive, and this is if Y is negative. So effectively, up to angular multiples of 2 pi being added to this, effectively, this is the formula you can use. Though most commonly in terms of derivations, we use the simplest form of it right there. I showed you last time that you could take a function z of two variables and replace x and y with r cos theta and r sine theta, and use the chain rule to ultimately find dz dr and dz d theta. That's what we focused on last time, but you actually can do it the other way around too. Maybe you've got a function best described in polar coordinates first, and you want to figure out its dependence on rectangular coordinates. Maybe you've got z equals f of r theta. It's just simplest to describe your function in polar coordinates at first, but then you want to figure out how it depends on x and y. Yeah, effectively, you can replace r with square root of x squared plus y squared, and replace theta with arctangent of y over x. Or maybe this more general kind of crazy thing here. It gets a little confusing. But just to keep it simple, pretend that works. Pretend x is positive. And get a function that depends on x and y. And you could try to figure out the partials of z with respect to x and y in terms of the partials of z with respect to r and theta first. You can use the chain rule effectively in the opposite order. The diagram in that case would look like this. You'd think of z as depending on r and theta first, and then r and theta depending on x and y. So you take the partial of z with respect to r, multiply it by the partial of r with respect to x, add the partial of z with respect to theta, and multiply that times the partial of theta with respect to x. And then with respect to y, you could do something similar, except replace the x's with y's. In both spots. And just like you could simplify these derivatives using these equations last week, so you can technically simplify these things using these equations. Again, for simplicity, assuming it's the arctangent of y over x one. I mean, the derivative of this one's going to be the same because adding pi doesn't have a different derivative. So for example, r being the square root of x squared plus y squared, which is x squared plus y squared to the 1/2, means the partial of r with respect to x from the chain rule is 1/2 x squared plus y squared to the negative 1/2 times 2x, which is x over the square root of x squared plus y squared, which should look familiar from the exam. And that, while it's true that's the derivative of r with respect to x, could also, using the fact that the square root is r, be written as x over r, which is kind of convenient. The partial of r with respect to y is something similar, except you get y over r in the end. Kind of convenient. How about the partial of theta with respect to x and y? Oh, I got to take the derivative of arctangent, I guess. Derivative with respect to y looks a little easier, but let's do it with respect to x first. I need the chain rule. Derivative of arctangent is 1 over 1 plus whatever's inside there squared. But then from the chain rule, I need to multiply that times the derivative of y over x with respect to x. Use the quotient rule. Low d high minus high d low, differentiating with respect to x over the square of what's below. I'm not assuming y is a function of x, so its derivative with respect to x is 0. This simplifies to negative y over x squared. Bring the negative y up top, multiply the x squared through the bottom here, it'll become x squared plus y squared. Do you see that? You multiply that x squared down there, it'll cancel with the x squared here. Have an x squared there. It'll simplify to that. And this is negative y over r squared. Kind of cool. How about the partial with respect to y? It's going to start the same, but then the derivative of y over x with respect to y is just 1 over x. Right? Differentiate with respect to y. Y is to the first power. 1 over x is a constant. You get that constant. Let's also, for the sake of multiplying through the bottom by x squared, multiply the top and the bottom of this by x, which doesn't change it because it multiplies it by 1. And it's going to simplify to x over x squared plus y squared. X over r squared. These formulas that I'm deriving are useful. And they also can help you derive strange looking things that are sometimes useful, like what I'm about to show you here, like this equation, which gives you the squared magnitude of the gradient vector in polar coordinates. Where does that come from? It effectively just uses the equations I just found. U, what is U? U is just a dependent variable name that I'm using here instead of z in this formula I've highlighted. Might be better to use the function name f instead of u, but it's somewhat traditional to use the variable name. U is actually a common dependent variable name in this context, especially when you're talking about partial differential equations. U is commonly used with partial differential equations. Could represent a temperature distribution. Could represent, like for a wave, could represent the magnitude of the wave or the displacement. This is useful for, you ever heard of Laplace's equation and the wave equation and things like that? That's where this kind of notation comes into play. We're interested in the gradient of u, which you could also write the gradient of f. It would be this vector. I could write both of those derivatives like this. And I could replace the partial of r and theta with respect to x and y with these things that I derived. I'm using u instead of z, but this is what I'd be using. Let's go ahead and rewrite it. So I'd get partial u partial r times partial r partial x plus partial u partial theta times d theta dx. Do the same thing with y instead of x. Looks pretty similar. It can be easy to get confused here and write something wrong. So I'm trying to be careful. And then again, you could replace these derivatives with the formulas that I just derived 5 minutes ago. Partial of r with respect to x is the same as x over r. So I could write x over r times the partial of u with respect to r. I'll just write that as u sub r. Partial of theta with respect to x, that was the negative y over r squared times the partial of u with respect to theta. I'll just write that. So this is going there and this is going there. Do the same kind of thing over here. Partial of r with respect to y is y over r times ur. The ur comes from that. Partial of theta with respect to y, that was the x over r. X over r squared times u theta. And then I could try to find the magnitude of this vector and square it. Taking the magnitude squared avoids square roots. So I got to square this thing. And add the square of this thing. I'm doing a dot product effectively of this vector with itself. Is this going to simplify nicely? It's not so clear. We might get some cancellation from outside and inside products here between the two terms. If I square this, I get x squared over r squared, ur squared minus, okay, the outside and inside products is going to give 2xy over r cubed, ur u theta. Last times last will be y squared over r to the fourth, u theta squared. I'm squaring just this thing so far. Square this thing, y squared over r squared, ur squared, plus 2xy over r cubed, ur u theta. These are going to cancel. That's awesome. And then plus square this last one, x squared over r to the fourth, u theta squared. Then combine, looks like I should probably combine these and factor out common factors. So it looks like I get x squared plus y squared over r squared, ur squared, plus x squared plus y squared over r to the fourth, u theta squared. And lo and behold, that's r squared. And this is r squared. So we get more cancellation. Completely cancel and partially cancel. ur squared plus 1 over r squared u theta squared. The ur and the u theta are derivatives, rates of change. The r itself is not a derivative. It's a polar coordinate. This kind of thing, weird as it seems, has got plenty of applications. You'll see if you take classes like maybe mechanics or maybe electromagnetism and that kind of thing. You'll see polar coordinates used a lot. It can be visualized. I'm doing it for a particular function here, x squared minus 2y squared. I'm trying to understand intuitively the meaning of this. What did this represent again? It represented the squared magnitude of the gradient vector. That's what it represents. take its square root to find the magnitude of the gradient vector itself. And so what I'm trying to show here, I know it's kind of small. These are the level curves of the function. Notice I've got the circle that's the radial at the radial coordinate of the point, and I've got the ray that's at the angular coordinate of the point. The graphs over here and here are the effectively taking the function of two variables and restricting it to the circle and the ray and seeing what the graphs look like. Notice theta is going from 0 to 2 pi. So I'm going around the circle, and r, the radial coordinate, is going from 0 out technically to infinity. And I'm seeing the behavior of the function. I did plot the gradient vector here, though it's kind of hard to see. It's this black arrow at this point. It is, you don't see the level curve at that point. I could move it to try to put it on a level curve more precisely. The gradient vector is perpendicular to this level curve here. It's pointing from dark to light at that point. We're interested in understanding the size of the gradient vector. And effectively, especially if we're at a radius r that's far away from the origin, r is large, what you can think of intuitively is that if r is large, this quantity is probably a lot smaller than this quantity. So the size of the gradient vector is more affected by the derivative in the radial direction along the blue line, the rate of change in the blue line, than it is by the derivative in the angular direction, theta. I don't know that that's so intuitive there. I mean, the slopes of these graphs, you could try to eyeball them. This slope looks like it might be in the ballpark of -20 or something, and this one more like -10. But evidently, it's this derivative, its magnitude, that affects this more. You'd have to move the point around and try different examples to see that more clearly. But that is a step toward trying to understand the meaning of this equation. And this equation, I can guarantee you would come up in an advanced physics class. Okay. This is showing you the process, the problem-solving process for doing this kind of thing. Polar coordinates is useful for more than just doing double integrals, as we're going to use it later in the course.